So hello everyone. So this lecture is about algorithmic strength reduction in filters and transform. And the purpose of this strength reduction is to reduce the strength in parallel FIR filter and discrete cosine transform. That leads to reduction in hardware complexity by exploiting the substructure sharing. So by now you have already learned about the parallel FIR filter. So suppose this is a system, this is a FIR filter and which is processing a sample xn and producing output yn, and if we want to increase the sampling rate, so one option is pipelining, second is using parallel blocks. So we can use L number of parallel blocks, similar parallel blocks. Okay, so we will give x of 0 to this, x of 1, x of L if we are using L number of parallel blocks, and the corresponding output will be y of 0, y of 1 and y of L. Okay, so to increase the sampling rate by L, we need L number of blocks, and if the area of this block is A, the area of this parallel structure will be L times E. So in other words, the circuit area increases linearly with the block size. So in many design situations, the hardware overhead incurred by the parallel processing cannot be tolerated due to the limitation in the designed area. Therefore, it is advantageous to realize parallel filter structures that consume less area than the traditional parallel FIR filter structures, and that can be done by substructure sharing. Okay, so in this there is no sharing of structures. Each sample is processed by independent FIR filter. So we will try to convert this filter in such a form that where it is possible to share the hardware. Okay, so as a result, the total number of blocks used will be reduced and the overall area will be less than the original area, that is L into E. So in this context, we will discuss the design of parallel FIR filter using algorithmic strength reduction transformation, and the method that we will use is polyphase decomposition. Okay, so formulation of FIR filter using polyphase decomposition. So this is also used in multi-rate signal processing. Okay, so starting with N-tap filter that can be expressed as yn is equal to hn convolution xn in time domain, and that can be expanded in the form of summation I equal to 0 to n minus 1 h of I and x of n minus I for n equal to 0, 1, 2 up to infinity. So we have considered xn as an infinite length sequence, and hn is FIR filter coefficients of length n. n. So this convolution can be represented in the form of multiplication in z domain. So we can write in z domain y of z is equal to xz multiplied by xz, where yz, hz and xz are z transform of yn, hn and xn respectively. Okay, so hz is given by summation n equal to 0 to n minus 1 hn z of minus n, and x of z is given by summation n equal to 0 to infinity x of n z of minus n. So hn is of length n and the length of xn is infinite. Okay, so I can represent xz as x of 0 plus x1 z inverse plus x2 z minus 2 plus x3 z minus 3 and so on. Okay, so now from this equation, separating even number terms and odd number terms, x0 plus x2 z of minus 2 plus x of 4 z of minus 4 dot 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 plus, so this is even number term, and separating the odd number terms, so x1 z inverse plus x3 z inverse z raised to the minus 3 plus x5 z to the power minus 5 and so on. Okay, taking z inverse common from this odd number term, so x0 plus x2 z minus 2 plus x4 z minus 4 plus so on, and taking z inverse common, I have x1 plus x3 z minus 2 plus x5 z minus 4 and so on, and this can be represented as x of 0 z square plus z inverse x of 1 z square. Okay, so where x of 0 z square corresponds to x of 2k in time domain, and x of 1 z square corresponds to the odd numbered sample, that is x of 2k plus 1 in time domain. So x of z square corresponds to even number sampled, represented by x of 2k, and x of 1 z square corresponds to the odd number sampled, represented by x of 2k plus 1 in time domain. And x0z is z transform of x of 2k even number terms and x1 z is z transform of odd number terms, that is x of 2k plus 1, and x of z is x of 0 z square plus z inverse x1 z square. So we can easily prove this relation. Okay, so let's take some random sequence xn that is given by values 3, 1, 5, 6, 2, 4, -3 and 7. Okay, so this corresponds to x of 0. So instances are 0, 1, 2, 3, 4, 5, 6, 7. So the z transform xz can be written as 3 plus z inverse plus 5z raised to power minus 2 plus 6z raised to power minus 3 plus 2z raised to power minus 4 plus 4z raised to power minus 5 minus 3z raised to power minus 6 plus 7z raised to power minus 7. Okay, so x0n, that is even number terms that are 3, 5, 2 and -3, and x0z is given by 3 plus 5z raised to power minus 1 plus 2 z raised to power minus 2 minus 3 z raised to power minus 3. And odd number terms x of 1n are 1, 6, 4, 7. So x of 1z is given by 1 plus 6 z inverse plus 4z minus 2 plus 7z minus 3. Okay, so x0 z square can be represented in the form half of x of z plus x of minus z. Okay, so x of z is this, and x of minus z will be 3 minus z raised to power minus 1 plus 5 z raised to power minus 2 minus 6 z raised to power minus 3 plus 2 z raised to power minus 4 minus 4 z raised to power minus 5 minus 3 z raised to power minus 6 and minus 2 minus 7 z raised to power minus 7. So if we add xz and x of minus z, so the odd number term will be cancelled out, and we have duplicate values of even number terms, so we divide by 2, and if we substitute z square in place of z in this equation, the result will be x of 0 z square is equal to 3 plus 5 z raised to power minus 2 plus 2 z raised to power minus 4 minus 3 z raised to power minus 6. Okay, and this will be 7, sorry. So x of z square is equal to half of x of z plus x of minus z. Similarly, x1 z square can be written as z by 2 x of z minus x of minus z. Okay. Okay, so combining these two equations, z will be transferred to left hand side and it will become z inverse. Okay, so x of z will be given by x is 0 z square plus z inverse x1 z square. Okay, so this identity is valid. Okay, so similarly hz can also be decomposed. So xz can be written as h of z square plus z inverse h of 1 z square. Okay, so h of 0 z square is even numbered, so filter of length n by 2, and h of 1 z square corresponds to odd numbered subfilter of length n by 2. Okay, so yz is the product of h of z and x of z, and substituting hz and xz by their odd and even numbered counterparts, we have h0 z square plus z inverse h1 z square, and similarly for xz I can write x0 z square plus z inverse x1 z square. Okay, so opening the brackets and multiplying the terms, I have x0 z square h0 z square plus z inverse x0 z square into h1 z square plus x1 z square dot h0 z square plus z raised to power minus 2 x1 z square dot h1 z square. And on the left hand side I can decompose yn into even and odd number terms, and in z domain I can write y0 z square plus z inverse y1 z square. Okay, so y0 z square corresponds to y of 2k, and y1 z square corresponds to y of 2k plus 1. So this is in time domain, this is in z domain. So now comparing the left hand side and right hand side, I can write y0 z square is equal to x0 z square h0 z square plus z raised to the power minus 2 x1 z square dot h1 z square. Okay, separating out the even number terms. So this is z raised to the power 0, this is z raised to the power minus 2, and y1 z square will be equal to this term, the coefficient of z raised to the power minus 1. y1 z square is x0 z square dot h1 z square plus x1 z square dot h0 z square. So in matrix form I can represent this equation. So on the left hand side y0 and y1 in a column matrix, in right hand side the filter coefficient h0 h1 z square h1 h0, and then the signal x0 x1. So this can be implemented. Okay, so the block diagram representation of these two equations is something like this. So I have filter E1 subfilter of length L by 2 given by H0, and even numbered sample, that is x of 2k, is being fed to it. Okay, and this is getting added by odd numbered of sample x of 2k plus 1, which is being fed to odd numbered subfilter coefficient given by h of 1 and multiplied by z raised to the power minus 2. So this is a delay that corresponds to z raised to the power minus 2. Okay, so since we have decomposed in even and odd parts, we have decomposed in two parts, so this can be considered as a two parallel system, and in two parallel system this delay, if input is xn, the output would be x of n minus 2. Okay, so this all are discussed in parallel processing. Okay, so this will be added to the output produced by H0, and the corresponding output is y of 2, that is even numbered sample output sample. Okay, for y of 1 z square, the even numbered sample is being fed to the odd numbered filtered subfilter, so x of 2k will be provided to odd numbered subfilter h1, and this will be added to odd numbered sample being fed to even number subfilter. Okay, so this x of 2k plus 1 will be provided to even numbered subfilter, and their output will be added. And the output will be even numbered, odd numbered, that is given by y of 2k plus 1. So this is two parallel filter representation. Okay, so this filter processes two input samples, x of 2k and x of 2k plus 1, and generates two output, that is y of 2k and y of 2k plus 1 every iteration. Okay, so now talking about total number of multiplications and additions required to implement this structure. Okay, so these filters are of length n by 2, and each sample x of 2k will be multiplied by n by 2 coefficients of h0, n by 2 coefficients of h1. Similarly, x of 2k plus 1 will be multiplied n by 2 times in this filter and n by 2 times in this filter. The total number of multiplications are, total we have 4 subfilters, and in each subfilter the multiplication will be n by 2, that is 2n. And talking about total number of additions, so these are n by 2 tap filters, and n by 2 tap filter will perform n by 2 minus 1 additions. So total number of additions will be n by 2 minus 1, that will be done by one subfilter, and we have total 4 subfilters, so into 4, and 2 external addition, or you can say post addition 2, so that is given by 2 and minus 1. Okay, so this justification of this is, suppose we have n terms like 1 2 3 4, let's say we have 4 terms and we want to add 2 terms at a time. Okay, so plus plus plus, so first addition, then second addition, and then third. So for n terms, n minus 1 additions are required. So for n by 2 taps, n by 2 minus 1 additions are required. Okay, okay, so now consider these two equations, that is given by y0 z square, x0 z square, x0 z square plus z minus 2 x1 z square h1 z square, and y1 z square is given by x0 z square h1 z square plus x1 z square h0 z square. Okay, so in short notation I can write y0 as x0 plus z raised to minus 2 h1 x1. This is shorthand notation, and y1 can be written as x0 h1 plus x1 h0. Okay, so this equation can be written in different form. So y1 is equal to h0 plus h1 x0 plus x1 minus h0 x0 minus h1 x1. Okay, so h0 x0 and h1 x1, this is common in y0 and y1, and these operations can be shared. Okay, so this can be shared by, this can be shared in this way. So we have a subfilter h0, second subfilter h0 plus h1, and third subfilter h1, and x of 2k will be given to h0, okay. So and x of 2k plus 1 will be given to subfilter h1 directly. Okay, so we have to generate x of 0 plus x of 1, so we will add the two signals, and the output of this adder will be provided to subfilter h of 0 plus h of 1. Okay, so h0 plus h1 dot x0 plus x1, that is generated at this point, and we have to subtract h0 x0 and h1 x1. Okay, so h1 x1 is the output of this filter that we will subtract from this. This will perform minus operation, and further we have to subtract x0 h0, so one more adder and subtract operation, and this output will be y of 2k plus 1. Okay, and x of 2k is h0 x0 plus z minus 2 h1 x1. So h0 x0 will be added to the output of h1 passed by a delay element d, and added to the output of filter h0. So this output is y of 2k. So this is reduced complexity two parallel FIR filter. Okay, just by rewriting this equation into some other form like this, we have reduced the one block, and indirectly we have reduced the complexity. Okay, so in this architecture there were 4 blocks, and in this architecture there are 3 blocks. So talking about multiplications and additions, okay, they are n by 2 sequences, and each filter will perform n by 2 multiplication. So 3 subfilter will perform 3 into n by 2. multiplications, that is 1.5, n, and additions. Okay, so again they are n by 2 length filter that will perform n by 2 minus 1 additions, and for 3 filter factor 3 will come, and we have one pre-addition and 3 post-addition plus 3, so that is 3 n by 2 minus 1 plus 4. Okay, so compared to 2n addition and 2n minus 2 multiplications, this is reduced value. So this technique that we have discussed just now is known as fast FIR algorithm, and this derived structure is also known as fast FIR filter.